Okay, so before the break, we spent quite some time working out the expression for acceleration, velocity, and displacement. We're going to use all of them for the next couple of minutes. Right. The first thing that we're going to do is probably the most important thing for the entire lecture. Okay, so just pay close attention to what I'm trying to do now. All right. So I'm going to write back to back the expression for acceleration, which is here. And then I'm going to copy the one for displacement up there down here. X of t equal to a cosine omega t. Okay, so what you realize is that for the acceleration, it's actually very close to what you have for displacement, because here this part of the acceleration is exactly what you have for the displacement. So in principle, I can substitute a cosine omega t by simply using x of t. So this gonna give me a, which is a function of time, equal to minus omega square that stays, and then times x of t, which is x as a function of time. So if you are even if you want to even like do a shorter equation, you can ignore the time dependent thing and then kind of remember that everything depends on time except for omega. So you can write a equal to minus omega square times x. And this is very important, because what it tells you is that the acceleration of the particle is proportional to the displacement with a minus sign. Okay, so for some of you, it's a little bit, you know, observant. You probably remember that we saw something very similar earlier when we talked about the Hooke's law for spring. Okay, so we're gonna do that very soon. But in any case, this is a very important equation, and this is true. This is true because we start from x of t equal to a cosine omega t. Okay, because that's what we start with, and then we just differentiate it twice, and then in the end this is what we got. Actually, this is true not only just for cosine, it's also true if you choose to be a sine omega t in the beginning. It's even true if you remember the starting phase phi, which we chose to be 0, right? If you don't, if you didn't choose it to be 0 in the beginning, you get the same result. So even if you use a cosine omega t plus some phase phi here, you're gonna get this equation nonetheless. Okay, and this is really cool because it means that if you have anything that satisfies this relation, then you can say that, okay, x has to be one of this form for sure, either cosine or sine or cosine of any phase, right? If this is true, then x is given by this. Okay, so I want to emphasize that not every oscillation looks like cosine or sine. Okay, this is a very special case. We kind of know that it's going to be sine and cosine because, I mean, it's the simplest case, but in reality, it doesn't always have to be this sine or cosine. Okay, so I will write it down here. So not all oscillations are sine or cosine. Okay, and in mathematics, we have the word, or in physics rather, if they are sine and cosine, we call that to be harmonic. So it's kind of maybe more user-friendly term to use, right? So essentially what I'm saying is that not all oscillations are harmonic, mean that not all oscillations are given by, described by sine and cosine, okay? But if that particular oscillations, if it obeys this equation, a equal to minus omega square x, then it is harmonic, meaning that the solution for displacement is sine or cosine. So we're gonna call anything that obeys this to be simple harmonic motion, which is a fancy name for saying that it's described by either sine or cosine function. Okay, so a simple harmonic motion or simple harmonic oscillation is the oscillation that is described, well, the displacement, the velocity, and the acceleration are described by either sine or cosine function. Okay, that's what we mean by simple harmonic motion. And mathematically, this is the simplest that we can have. Okay, so anything more complicated than this, then it's not going to be harmonic. So it's not going to be described by sine or cosine. Okay, a few property of simple harmonic motion. First of all, again, let me write it down again. A must be equal to minus omega squared times x. Okay, this has to be true. The other thing is that omega, remember what is omega? Omega is the frequency, is the parameter that's telling you how fast it's oscillating. Okay, omega is independent of the amplitude. This is not always the case in real life. Okay, but in the simulation that we show at the beginning of this class for the mass and spring, if you do small oscillation, small amplitude of the oscillation and large amplitude, the frequency is the same, right? How many cycles it completes in 1 second does not matter if you start it with very tiny amplitude or very large amplitude. So omega is independent of the amplitude. That's another important um, property of simple harmonic motion. And again, in real life, this is probably not going to be the case, right? So sometimes when you change the amplitude of the motion, it will change the oscillation frequency, right? But if you have simple harmonic motion, then this is the case. Okay, and the other thing is x of t, v of t, and then a of t are either described by cosine or sine, or cosine with the phase factor, right? So that's the kind of the consequence of this being a simple harmonic motion here. So that means if whatever you do when you're trying to analyze your system, you end up having the equation that looks like this, then you can say right away that, okay, it's a simple harmonic motion. And not only that, you can just read off what's the oscillation frequency because that's given by omega. And that's exactly what we're going to do for the spring system that we had in the beginning. So let me go back quickly to the first page. So remember we have this Hooke's law, which relates the force by the spring on the mass. as a function of the displacement. Okay, so let's do some more to that Hooke's law. So from Hooke's law, we have F equal to minus kx, but we can use Newton's second law of motion. So Newton's law that say F equal to ma. Right. So you can put this into Hooke's law and then get this equation of motion, which is ma equal to minus kx. And if you rearrange a little bit, you have this equation, which is acceleration is minus some constant here times the displacement. So if you compare this to the equation for simple harmonic motion, which is this one, it looks exactly the same. So compare to a equal to minus omega square x. And you can see that a is here on the left hand side, x is here on the right hand side, and omega square is this constant. So this tells you two things. First of all, it tells you that the mass attached to the spring move in a simple harmonic motion, right? So it's describable by sine or cosine, or sine with some phase or cosine with some phase. Second, it tells you that omega square is k over m. So that means omega is simply square root of k over m. So this tells you that the frequency of this oscillation, which is the mass and spring system, depends only on two parameters, the spring constant k and the mass m. And again, it confirmed the other point, which is omega, which is the frequency of the oscillation, does not depend on the amplitude of the oscillation, because there's no amplitude in omega here. Okay, so we have really quickly determined the frequency of the mass and spring system, right? So if you don't like omega, then you can convert it to frequency, and you should confirm yourself that it's going to be given by 1 over 2 pi k over m, and the period of the oscillation is 1 over f, so it's just 2 pi root m over k, like this. Okay, so this is usually the way for for you to figure out, okay, this kind of system, what is the oscillation frequency. So trying to put it in this form, and then you can read off omega right away. So the other system that we're going to briefly talk about is the simple pendulum. So a pendulum is a swinging mass, right? So it's a mass that is attached to the ceiling, and then what you do is you maybe displace it like this, and it's gonna swing back and forth. Right? So we're trying to find what is the frequency of this pendulum swinging using the same principle that we did earlier. So we're gonna try to put everything in this form, and then we're gonna read off omega. But it's gonna be a little bit different. So this might be not totally clear to you in the first hearing. So just go back and then try to understand this later. Because it's kind of like, well, the motion of the pendulum can be described as the rotation about this pivot point. So this This should remind you something about, like the moment, the talk or something that you study in last semester. Okay, so what it means is that I can use this angle here to describe the location of the mass. Right? So instead of a displacement, I use what we call the angular displacement, theta here. Okay, so theta is the angular displacement. And what we want is alpha, which is angular acceleration. So in terms of calculus, that's just the second derivative with respect to time of the angle theta here. And that's equal to what we call the angular acceleration. And last semester, hopefully you have seen this. That's what we call alpha 4. Okay, so what's the equation that we use to describe the rotation? Is torque equal to I alpha, right? And remember, this torque is force time distance. This is the moment of inertia, and this is the angular acceleration we just wrote down earlier. So in this case, we need to consider gravity, G, pointing down. So the force that is causing the rotation is the gravity mg here. And another thing we need is the length of the pendulum, which is L. Okay. Um, one thing that you can see is that if the angle is going that way, meaning is counterclockwise, okay, so the angle is rotated this way counterclockwise, the torque is trying to rotate it back. So I write it down here. So angle is counterclockwise, but torque is clockwise, right? Clockwise is rotating that way. So torque is trying to rotate it back to the center position, which is angle equal to 0. And that's kind of very similar to the case for spring, right? Because spring is trying to push the mass back to the center position. Here is the same. The torque is trying to rotate the pendulum back to the center position. So this allows us to put in a minus sign because torque and the angle here is always the opposite direction. If one is clockwise, the other one is counterclockwise. If one is counterclockwise, then the other one is clockwise. Right? So putting things together, what is torque? Well, torque is mg times sine of the angle. Okay, so make sure you know why is sine, is not cosine. And that's going to be equal to minus, okay, minus sign is coming from what we just said earlier. I is the moment of inertia, which is the mass of the pendulum, times the distance to the pivot point, which is L square. Oh, and actually I forgot. Torque is mg, also you need to multiply by L. Okay, because torque is force time distance, so mg alone is just the force. So you need L here also. And then times alpha, which is the angular acceleration. So you can see that m cancel out. So you have alpha equal to minus g over L times sine theta like this. Now this is something that is different from what we maybe expect or what we have seen before, right? So if we want to claim that this pendulum motion is simple harmonic, what we want is alpha is equal to minus omega square times the displacement, in this case angular displacement, but anyway it has to be just the displacement. So it has to be theta, but we don't have theta here, we have, instead of theta, we have sine of theta. So it's not exactly the same. It's not exactly what we want. So in general, a pendulum is not simple harmonic because the equation that you got from pendulum does not match exactly what you expect for simple harmonic motion. Okay, so I'm gonna write it down that this is not the same form. Okay, so pendulum is not simple harmonic motion. Okay, it's not simple harmonic motion. However, in the case of small angle, however, if theta is small, and now you're gonna debate, okay, what do you mean by small? Well, that probably depends on your criteria. But roughly speaking, if it's probably less than or equal to, like 10 degrees or something like that, okay, then sine of theta is approximately theta. And if you don't believe this, you can try to verify this with your calculator. But theta has to be in radian. Okay, in degree it doesn't work. Okay, it has to be in radian. So if you put in theta equal to like 0.01 radian, you're gonna see that sine of 0.01 is very close to 0.01 itself. So that means if the angle is small enough, this equation here can be approximated. Okay, in physics we do a lot of approximation because in real life things gonna be a lot more complicated than our theoretical analysis. So with this small angle approximation, then this equation becomes alpha equal to minus g over L times theta instead of sine theta. Okay, this is the approximation. And usually it's good enough if the angle is less than or equal to 10 degrees, right? Which is maybe some of you have done some experiment with pendulum. One thing is that you are informed that don't swing it too large of the amplitude because then this approximation will break down. Okay, so if this approximation hold, then we have this equation to be in the form of alpha equal to minus omega squared times the displacement, which is now simple harmonic. And omega is simply given by square root of g over L. Okay, so a pendulum with this approximation, this is called a simple pendulum. Okay, so some of you might have seen this before and then might ask like, why do we need to put in the term simple here? It's simple because we do one approximation in the analysis, which is small angle, right? If you don't do this, the pendulum is not simple. I can tell you that the solving this differential equation is a lot harder than you probably expect, right? So just one simple approximation here, it makes things 100 times, million times easier because now it's becomes simple harmonic motion and we can just read off omega, which is the frequency of the pendulum right away. So omega is square root of g over L. Okay, so simple pendulum means a pendulum with small angle or small amplitude. So strictly speaking, a pendulum is not simple harmonic. But if the angle is small enough, then it's approximately simple harmonic. Okay. Next thing that I need to talk about is the energy in simple harmonic motion. And to do that, I'm gonna go back to the mass and spring system because that's the simplest. Okay. Anytime that is moving, there are two kinds of energy involved in the system. One is kinetic energy, so total energy, E total, come from two contributions, kinetic part and potential part. Okay, and this potential energy is not mgh. We ignore G in our analysis here. It's the potential energy of the spring. So it's the elastic potential energy of the spring, okay, not the gravitational potential energy of the system. So there's no mgh in our analysis here. So we only have these two terms, and you know the formula for each one, which is 1/2 mv squared for kinetic energy, and for elastic potential energy is 1/2 kx squared. Okay, v is the velocity, x is the displacement. And both v and x we have calculated before. So v is, well, okay, maybe I should write x first. So if we're going to use x to be a cosine omega t, then v is going to be minus omega a sine omega t, right? Just one differentiation, you're going to get the velocity. And then you can put it, do some barrier here, and then you can put it in this equation for energy. So we're going to have 1/2 m, well, v squared is going to be omega square a square sine square omega t. Okay, just a direct substitution. That's for the kinetic energy, and for the elastic potential energy is 1/2 k x squared, so it's a square cosine square omega t. All right, and what we're going to do is we're going to use the fact that omega square for spring is k over m. This is what we got earlier, right? The frequency of the oscillation for spring is given by this, right? So I'm going to substitute omega into that part, the kinetic energy part, and I'm going to have 1/2 m. Omega square becomes k over m, so m and m cancel out, and then a square stay the same, sine square omega t stay the same, and then for the elastic potential energy part, nothing changes. I have not done anything. But you can see that now the term in front and the term behind, they contain the same factor, common factor, which is 1/2 ka squared. So I should be able to take it out in front and then write the remaining in the parentheses or pair of parentheses like this. Okay, so a simple algebra, that's what we have here. And for those of you who remember trigonometric identity, you know that sine square plus cosine square of the same angle, that always gives you 1. So this bracket always gives you 1. So in the end, what we have is E total, which is the total energy of the system, is simply given by 1/2 ka squared. And it does not depend on time because, well, the total energy is always conserved. Unless you lose energy, then the total energy might decrease with time. But under ideal circumstance, you don't lose any energy, so the total energy is always given by this value. Okay, and this total energy sometimes is all in kinetic part, sometimes it's all in the elastic potential energy part. You have this transfer of energy back and forth between the two energies. That's fine, but when you add them together, they have to be the same, which is 1/2 ka squared. And you can see that different amplitude of the oscillation simply give you different energy of your oscillation. So if you increase the amplitude, then you're putting more energy into the system. But again, changing the amplitude does not change the frequency of the oscillation. Okay, so the frequency of the oscillation is independent of the amplitude, which is a very important property of simple harmonic motion. Okay, so for the last few minutes, let's just talk about the case where you might have energy loss, right? So in that case, you're going to have what is called damp oscillation. And again, we are not going to talk too much about the mathematics behind this because it's going to involve quite a lot of differential equation solving. So we're not going to do that. So we're going to describe this, you know, qualitatively only. So damp oscillation is the oscillation with energy loss. So that means the total energy is not going to be always 1/2 Ka squared. It's going to get lower and lower, and eventually it's going to stop moving. So when you draw the graph, okay, it kind of looks like a regular sine-ish oscillation in the beginning, but the amplitude going to get smaller and smaller and smaller like this. And that's actually what you typically see in real life all the time, because again, in real life it's very hard to find ideal oscillation, right? So this decay in the amplitude is usually given by this kind of envelope. So it's kind of like the boundary, this dashed line. And usually this dashed line is given by exponential decay function. Exponential decay function, okay, which indicates that um, the the mass, in case we are talking about mass and spring, the mass lose energy over time, okay, and it's going down exponentially like this. Okay, so just for reference, you don't need to remember or anything. The equation for x of t then can be just a normal cosine oscillation or sine oscillation, but with the modification of the amplitude. So this is the decay in the amplitude. Right, that's what gives the exponential decay in this graph. And then maybe I'm gonna use sine here in this case. So sine omega t, something like this. So the only difference is the amplitude is not constant in this case. Right? But again, this is just for reference. You don't need to remember this. So if you don't do anything, you let it go, um, the oscillation gonna die eventually because you just keep losing energy. So how do you make sure to sustain the oscillations? And sometimes that's what we want, right? We want to sustain the oscillation of something, for example, the rotation of the fan, the rotation of the car engine, right? So you cannot just let it die and then just live with it because that's not what we want. So if you lose energy all the time, you can compensate for that by putting in extra energy all the time also. And that's what we call forced oscillation. So forced oscillation is the oscillation with external drive into the system. Right? For example, in the case of mass and spring system, instead of leaving the mass and spring to just oscillate and then eventually dies, you're gonna shake it. And how do you exactly do that? That's another question. But you put in some oscillating external force onto the system. Right? In terms of the car, the engine which is providing that extra external force here. It's trying to keep the oscillation going. Okay, and so essentially what we are trying to do is to compensate energy loss, E loss, by injecting energy external into the system. okay? And eventually, you're gonna be able to sustain the oscillations. But again, this is a little bit beyond the scope of our course here. But it's just something that you should know that the eventually the equation for the oscillation is gonna be cosine of omega prime t plus something, right? So the difference here is that when you put in some external, force to keep the oscillation going, the frequency of the oscillation here, this one is the frequency, so this depends on the frequency of the external force. Which is different from a free oscillation, right? So remember, if we have just a mass and spring and we let it oscillate freely, then omega is given by square root of k over m. But if you have force oscillation, you put in extra external force, which is trying to, let's say, check it. Eventually, the frequency of the oscillation of the mass itself will be the frequency of the force that you're putting in. Right. So force oscillation, you can actually control the frequency of the oscillation, because that's just up to you. It depends on how much you are shaking. Right. So force oscillation is very different from free oscillation in the sense that the frequency of the oscillation is determined by you as an external influence to the system. Okay, so I think that's all I want to talk to you today. Next time we're gonna start talking about wave. Okay, so we're gonna see like how we build upon like all of this, simple harmonic motion concept into wave, which is a collection of many oscillators altogether. Okay, yes, like this. Okay. All right. So if you have any question, then please ask. If not, I will see you all on Wednesday. All right. Take care, everyone, and stay safe.